The question you see right now on the screen looks very easy if we have an intuition, but that gives us incorrect answer. Let's see why. Consider a uniformly charged hemispherical shell shown below. Indicate the directions, not magnitude, of the electric field at an off-center point P on the drumhead of the shell. The most basic intuition we can have here is to see effect of this elemental ring at a point P. Or perhaps we can further divide this into even smaller elements and see effect by each one of them. For simplicity, we assume these elements as small point charges with charge dq. Recalling Coulomb's law, we are not surprised that the charges which are closer to point P exert more field than those far away. Thus, the net field in this plane is not zero, and it appears to act towards center. If we do the same for charges somewhere in the bottom, they will add an extra vertical component to P, means there indeed exists a horizontal component, so the net electric field vector must be somewhat tilted to a center, making option B correct. But no. We will come back on this method a little later. First, let's see a more intuitive way. Let's assume some general direction of field at P. If we make a copy of this arrangement and flip it upside down, we will have a hollow sphere with point P inside it, and field at P somewhat like this. It's kind of like mirror image of original hemisphere. But the field inside a hollow sphere is zero everywhere, means at P as well. And this is true only when we assume field at P due to these individual hemispheres to be vertical, so that they cancel each other out. And that is why option C is correct. This was the correct approach for such question. Well then, what went wrong in our first approach? Did Coulomb's law fail? No, it did not. The fact that we assumed these tiny elements to be point charges was incorrect. It is clearly somewhat like a curved square, so it is not a point charge. Let's fix our approach. Suppose the surface charge density of this hemisphere is sigma. So the total charge on this element would be sigma times its area. To find the area, we will use the solid angle subtended by this element at center. Thus the area is r squared times d omega. So using Coulomb's law, when we plug in dq in it, we get a very surprising result. The field is constant. It does not depend on distance between element and that point P. For simplicity, I am showing result due to center, but the same is true for point P as well, if we calculate. So every element has equal field at P, thus the horizontal components cancel each other out and only the vertical ones survive. And that is why the field is vertical.